Solis-Ocampo, Lab 4, Oscillations. Introduction. So the purpose of this lab is to investigate the motion of a spring mass system with the mass oscillating in an arc in the spring in a fixed point. And the goal of this is to predict the motion of the spring using the fundamental principles we know in order to compare the computational model to the observed motion and see if it follows the energy principle. We want to see if the total energy equals 0 in the spring, and we want to see if it follows closely to the computational model to see if all of our forces are correct. Some fundamental principles used is Newton's second law. The net force is changing based on the object's velocity, and more mass an object has, the more force is needed to move it. The gravitational force and attractive force between all objects that have mass or energy, and the bigger mass, a bigger force is needed. And the energy principle. A system's change in energy is a sum of work done by surroundings and thermal energy exchanged with the surroundings. Some of the equations use the average velocity formula to get the initial velocities, the two position and velocity update formulas in order to update the mass's position along the model with the spring, and Newton's second law, F net equals dp dt, or the change in momentum formula in order to see all the forces adding up. And the other one is the gravitational force, negative mg j hat, and the energy principle, which is the total energy of the system equals the work of the surroundings plus Q. And we also needed some work and power formulas in order to see how much force was actually being used upon the system. Here is our experiment. The initial condition: the system is the hanging mass and the surroundings is the spring, earth, and everything else around it. Here is the mass, and it is released from that point. The initial positions are as follows: this one in the x and that one in y. And the velocities, the initial velocity was calculated by using the average velocity formula with two specific points. And here's the motion of the x observed, and here's the motion of the y observed, showing that it shows a total energy of 0 at the end, total change of energy of 0. Here's some checker data. Here is the x column, and here's the y column. And again, this was the initial positions, and I got the initial velocities by using one of these two and subtracting it from here, from one of the first ones, and dividing it by the time it took. Here's some of the glow scoop results. So the model is in blue and the experiment is in red. As we can see, the model is following really close behind the experiment, but just not quite yet. And this just shows that the model and experiment both have deviating values towards the end of it, and but although it does, they also show that the total change in energy was 0. Here's some glow script review. Here's the G 9.8, the spring constant which was given to us, and the relaxed length of spring, which is found out with one of the spring formulas. And here's the equations for the spring, for the ball position and all that, the L hat. And here's the equations for the system energies, K, UG, US, and then the total energy is all of those different energies added up: the kinetic, gravitational potential, and spring potential energy. Here we are over here defining the initial energies in order for later on to calculate the change in forces. Here's some more: the F gravity, which was in the y position and negative, and the F spring, which was with the formula, and F net, which was both of those together. And here are the update formulas in order to update the mass. And here is some more code for the spring and all that, and here's for the calculating that changes in energy with the final and initial energies. Some sources of error could be incorrect initial velocities, uncalculated outside forces because the system isn't fully oscillated, and issues in computational model and positioning in tracker. I also could have had some calibration errors while doing the tracker system. So is the energy principle satisfied? Yes, it is. The graph shows that the total energy throughout the mass's movement is constant, and since there is also no external force, the change in energy is 0, demonstrating the conservation of energy and that the energy principle is satisfied. We can also see here that the delta K keeps on moving and it doesn't deviate and keeps on going back, showing that this net energy was 0. Continuing, we estimating the oscillation periods. For tracker, the delta t in between steps is that number, and for the x graph, peaks are about 6, 24, 41, 48 data points, with there being points repeating every 17.4 data points. To find t, the period of x, we multiply the amount of space, 17.4, by the step interval and get that x period is 1.65 seconds. For the y, it is the same, but y positions repeat every 16 points. Multiplying that by 0.09497 gives a period of about 1.52 seconds. The x position gives slightly larger periods than the y by 0.13 seconds more. And here's some of the graphs for the oscillating purposes, and these are the ones I got the data points from. And yeah, thank you.